to is in the space that we're talking about, so it would be considered a complete.
Give an example of continuous functions whose sequence of continuous functions whose limit is not continuous. Well, let's say whose limit is a step function, just approximate step function by a sequence. Just graph, don't try to form it.
Sure. So then if we have functions that do something like this, as n grows, you know, say this is n equals 1, this is n equals 2, and the limit, if this limit function is something like this, well, this is no longer a continuous function, so...
Which means that the set of continuous function is what?
It's not complete.
Not complete, right.
And then the next definition I'll write has to do with the set of normed spaces that are complete. And so, at least from my understanding, the reason we care about this vector space definition and the reason we care about this completeness is so we can bring the tools of analysis and linear algebra together to discuss these spaces of functions.
Well, one point I want to make is that this notion of completeness depends on the norm. Some same space could be complete in one norm and not complete in another norm, like this functions, because the notion of a Cauchy sequence depends on the norm.
Right. So when we say a normed space, we don't just mean a vector space, but we mean a vector space with a specific norm. So a normed space V is called a Banach space.
Banach space.
If it is complete. So these are the space of Sobolev functions that we had written is a complete. So you're pronouncing it differently, Banach?
Banach space.
Okay.
L2 is complete.
Right, so the continuous functions are not complete, but this L2 space that we defined, and I sort of said it was a subtlety that we were talking about Lebesgue integration. Well, part of that is we want functions, well, and this is of course Riemann integrable, but I can write sequences of continuous functions that do not converge to continuous functions, even if they are close to each other, even if they even if they can be written as a Cauchy sequence. But in L2, all of those Cauchy sequences, all of things like this, will converge to an element of L2. So it can be viewed as a Banach space. And there are a couple theorems and a couple results here that I'm probably going to skip. We have monotone convergence. I think the last thing I'll talk about is
Why do you talk about inner product?
That's what I was thinking.
And Hilbert spaces.
So another structure we can define on a vector space. So given a vector space V, we can define a binary operation.
It's not a binary operation.
I'm sorry.
The product is not
a
a
binary
number.
Function.
A map, I mean.
Yeah.
When you say we can define, not always you can define. I mean, a vector space V is called an inner product space if it has it. But not on each space you can define it. It's just not there.
So I'm just trying to think of the simplest one. Sure. So a vector space with the following map, or so from a vector space cross itself to R defined by.
Or here, not necessarily R. Here F. Yeah, here it could
That's
be
what I was
complex.
screwing up earlier. Okay. And so instead of making this a general field,
Complex.
do complex numbers, because that comes up in the definition. So again, we assume two vectors from whatever space we're considering, and we assume a scalar, a complex scalar. And then here's another place where I'm not going to remember the axioms. So we want,
So a map is called an inner product if it satisfies. So the first is bilinearity. It's linear in each argument, right?
well, sesquilinear, right? Because it's complex linear.
Yes, yeah, you're right.
So, so it has to be sesquilinear, which means that if I add vectors in one component, so I have this additive linearity in both the first and the second component. I won't write it for the second, but if I added two vectors here, I could again separate it. And then the important distinction of this word, if this field was R, then it would be...
Not all, you forget about these scalar multiples. If you
Right.
multiply by a scalar.
Right, so if I have a vector here, and then we have the difference between mathematicians and physicists, the mathematician will say it's linear here. Whereas in the second component, the reason I say sesquilinear for the field C is because we take the complex conjugate here. And then again, physicists will put the complex conjugate on the other. Physics notation is to put the complex conjugate on the other side.
And the last property,
Ah, right.
the complex conjugate of the inner product.
Okay. This is
The other word, V2, V1, V2. No,
Right.
V2 from. So in real space, it's just symmetric.
right. Yeah, so the antisymmetry and this complex conjugate in the second component, not antisymmetry, but conjugate symmetric, come out of defining our field to be the complex numbers. So this notion of inner product is sort of, I don't know a very good way of explaining it geometrically, but it's discussed again in the introductory courses on linear algebra.
Well, that's a scalar product of vectors, that's correct?
Sure.
Dot
So-
product.
Right, that's right. The dot product in Rn is an example of an inner product. So again, in this infinite dimensional sense, the functional analysis that we want to look at is...
Give an example in terms of sequences and functions of an inner
Okay.
product. Like
So-
on little L2 and the capital L2.
So again, this was the L2 we were discussing. If we say that x1 and x2 are in L2, then we can define an inner product.
That's not a good notation. Call it X and Y because you use indices for this.
You're right. So again, I'll write x is equal to, well, x is the sequence,
Sequence, right.
and then y is this sequence. Then an inner product here would be something like, sorry,
That's right.
yeah, and then, is that correct?
Yeah, well, it depends whether you're a physicist or
Ah,
not a
right.
mathematician.
Okay. Okay.
Okay.
So sorry for the handwriting. But again, if we multiply the components together, this will still give us, a finite number as long as these two sequences are in L2.
And it satisfies all these properties. So
Right. And we can't do this, and then there's some clever proofs of this I won't go through. LP is an inner product space if and only if P is equal to 2.
Right.
And we cannot define an inner product, even a more complex one, on any of the other spaces. So then if we talk about F1 and F2 from this capital L2, we can define their inner product. Kind of like how we define the norm.
Change your mind.
Oh, man.
Yeah.
I've taken too many mathematical physics classes. Okay.
No, you don't need that.
Yeah.
That's inner product.
For each.
Integral from 0 to 1. Well,
Again, if we're talking about that L2 from 0 to 1, it would be from 0 to 1.
yeah.
Or it would be over the manifold or whatever subset we're talking about.
Right.
But anyway, hopefully these spaces aren't too unfamiliar to everyone. Okay, and we can discuss their properties. And then the definition, the space that's used most commonly is...
How does it define the norm if you have an
Oh, right.
product that is
And then if
mentioned?
we have, well, I'll just put that here. So an inner product induces a norm. By saying that the inner product of a vector with itself is the norm of that vector squared.
Right.
So by this equation. And there is a subtlety here as well. When we are discussing a vector space, it's very general, or an inner product space. We could be talking about a norm different from the induced norm, and we could also have that inner product. But as far as I've ever seen, when we're discussing an inner product, we use its norm this way because that's the most useful relationship. I can't think of any examples when we would do it otherwise. And then the last definition, I won't write it, but just that is a Hilbert space is a Banach space where...
The inner product space.
Okay, sure, is an inner product space that has all of the properties of a Banach space.
That is complete.
Is complete, right.
So Hilbert
Is the
space
only
is a
difference.
complete inner product space.
Right. So that was all I had prepared for today. There are some other things in functional analysis that are kind of important, specifically
If
operators.
that would be all in function analysis, I'd be surprised. There are
Yeah.
some other things, just a few. Just a
So, to be very, very specific, there are some other things in a brief review of functional analysis that
There
I've
are
left
lots
out.
of other things.
So, this is maybe the first few days of a functional analysis course summarized very briefly. We could define, as we do in linear algebra, we talk about operators. We could define
So
all
what
of
the
those.
operators? Operators of mapping from a
Mappings.
vector space to vector space, right?
Right. And then specifically, we could discuss endomorphisms, where we have operators acting on a vector space to itself. We could discuss functionals, the key word in functional analysis, which are mappings from a vector space to the space of scalars. So the norm is an example of a functional. And functionals turn out to be very important. And we could do
Why
this
do we
for-
care about operators?
Oh, because things like integral equations, well, the integral could be viewed as an operator in some sense.
Yeah, the differential
And the differential
operators.
operators. Right. So again, all of this language of functions and the analysis kinds of things that we like doing with differential equations can be posed as operator theoretic kinds of questions.
And we start talking about spectra and resolvents and grid
Right.
functions and all that stuff. Yeah.
Right. So I don't know how much more of this we really need. He uses a tiny bit of it, well, and particularly the definition of L2 and sort of the notion of completeness there is important when we talk about the Fourier transform. Again, I'm not sure how much detail we'll go into that, but that's all I have now. It might be a good idea to discuss what we want to do next semester. I think it would be very useful if we did start with chapter 3, which is on the Fourier transform and parabolic equations and Fourier